All right, so in this section, we are going over 2.2, the limit of a function. And again, we're just reading through the textbook. So the learning objectives are using correct notation. We want to describe the limit of a function. Okay. Use a table of values to estimate the limit of a function or identify when the limit does not exist. All right. Use a graph to estimate the limit of a function or to identify when the limit does not exist. This is, we'll commonly use a graph to estimate the limit of a function. Define one-sided limits. We need to know what those are and provide examples. Okay. Explain the relationship. It is very important that you know how to explain the relationship between one-sided and two-sided limits. They are very related, and you need to know that relationship. Using correct notation, describe an infinite limit. Okay, infinite limits we are going to look at a lot. So we need to be able to describe those. And then finally, vertical asymptote. You already know what that is, or you should know what that is. We are going to talk about it today in terms of limits. All right. So the concept of a limit or limiting process essential to the understanding of calculus has been around for thousands of years. In fact, early mathematicians used a limiting process to obtain better and better approximations of areas of circles. Yet the formal definition of a limit, as we know and understand it today, did not appear until the late 19th century. We therefore begin our quest to understand limits, as our mathematical ancestors did, by using an intuitive approach. At the end of this chapter, armed with a conceptual understanding of limits, we examine the formal definition of a limit. All right. All right, so we're going to start with an intuitive approach and then look at a formal definition, which we won't pay too much attention to that formal definition. If you're a math major, you might see it more later. But we do need to know a somewhat basic definition, which is still pretty good. We begin our explanation of limits by taking a look at the graphs of the functions f of x equals x squared minus 4 over x minus 2. And we can see that's basically a line with a hole in the line where x is equal to 2. It makes sense that when x is equal to 2, you can see that f is undefined. The function g of x equals the absolute value of x minus 2 divided by x minus 2, also undefined at x equals 2. And then finally, h of x, which is equal to 1 over x minus 2 squared. Again, undefined at x equals 2. So all of these functions are undefined at x equals 2. All right. So they're all shown in figure 2.12. In particular, let's focus our attention on the behavior of each graph at and around x equals 2. So even though they're all undefined at x equals 2, they all behave differently at or near x equals 2. Each of the three functions is undefined at x equals 2. But if we make this statement and no other, we give a very incomplete picture of how each function behaves in the vicinity of x equals 2. To express the behavior of each graph in the vicinity of 2 more completely, we need to introduce the concept of a limit. So the intuitive definition of a limit. Let's first take a closer look at how the function f of x equals x squared minus 4 over x minus 2 behaves around x equals 2. In figure 2.12, as the values of x approach 2 from either side, the values y equals f of x approach 4. So you can see that, what they're saying here is basically as the x values get closer and closer to 2, notice the function is getting closer and closer to a y value of 4. Whether you approach from either side, right? If you approach the x value of 2 from the right-hand side, meaning from values greater than 2, then we still approach 4, but coming from a different direction. Either way, we're still approaching the y value of 4. Mathematically, we say that the limit of f of x as x approaches 2 is 4. And symbolically, we're going to express this as, so again, we're going to express this as the limit as x approaches 2 of the function f of x, that limiting value, even though we are, the function is not defined at 2, the limiting value is 4. Okay. From this very brief, informal look at one limit, let's start to develop an intuitive definition of the limit. We can think of the limit of a function at a number a as being the one real number L that the function values approach as the x values approach a, provided such a real number L exists. Stated more carefully, we have the following definition. And let's go ahead and just kind of write down what they said, in this paragraph here for this problem. Okay, so the limit as x approaches 2, and notice x approaching 2 is what we've already drawn down below, right? We're coming in closer and closer to 2, right? As whether we approach from the right-hand side or the left-hand side, the x values as they approach 2, what does the function do? The function goes this way or this way, depending on which way we're approaching 2 from. But either way you come from, the limit of this function f of x is equal to a y value of 4. Okay, so let f of x be a function defined at all values in an open interval containing a. So in our case, a was 2, right? So with the possible exception of a itself, so the function might not be defined at a, just like our f of x wasn't defined at 2, and let L be a real number. If all values of the function f of x approach the real number L as the values of x not equal to a approach the number a, then we say that the limit of f of x as x approaches a is L. More succinct, excuse me, as x gets closer to a, f of x gets closer and stays close to L. Symbolically, we express this idea as the limit as x approaches a of f of x equals L. And I'm sure we'll see pictures of this coming up pretty soon. We can estimate limits by constructing tables of function values and by looking at their graphs. The function values, that works. But also by looking at their graphs, that's a really, really good one. It's a really good way to find the limit. This process is described in the following problem-solving strategy. Okay, so let's go ahead and go through this problem-solving strategy, evaluating the limit using a table of function values. To evaluate the limit as x approaches a of f of x, we begin by completing a table of function values. We should choose 2 sets of x values. One set of x values approaching a and less than a, and another set of values approaching a and greater than a, right? So we should approach our value a. So let me sketch a function here because they haven't sketched one yet. Yeah, I thought they would have one, but I guess not. Let's just sketch a quick function here, right? And then here is a function, something like this. And here is x equals a. Right, there's that point. And then here is y equals L, right? So as we get closer, I'll do one in red, as we get closer to a, so, and maybe I should have done it in blue since I made the box in blue. So we're going to choose a set of a values approaching a and less than a. So in this blue line, all of these values on this blue ray here are approaching a and less than a. And the other set of values are also approaching a, but greater than a. And so we're approaching a from both sides. And what we want to do is, or hopefully, What we want to see is that, well, as we do that, our function approaches some value, right? So notice we are approaching this value here. And so as the x values gets closer and closer to an x value of a, what do the y values do? And of course, my sketch is a little bit off. The y values approach some y value of L. And if that happens, then we say that the limit of that function as x approaches a is L. Okay, so how would we make this table? Well, we're going to choose a values. We're going to choose a minus some number like 0.1. And then we want to get closer and closer to a, so then we can choose a minus 0.01. That's closer to a. Even closer to a is a minus a smaller number and a minus a smaller number. These are getting closer and closer to a, and they're all less than a. So these are all x values. So then what do we do with these x values? We plug them into the function. We plug each of these into the function, and then we might see a pattern emerging from these function values. Maybe these function values are all approaching. You see that they're getting close as you go this way, where the input is closer and closer to a. Maybe the outputs are all getting closer and closer to 4, as we saw in our previous graph. Okay. And then we do the same thing on the right-hand side. A plus some small value like 0.1, and then a plus a smaller value, and a plus a smaller value, and then a plus an even smaller value. What do we do with all of these inputs that are getting closer and closer to a? We plug them into f and see if there's a trend with these function values. Are these function values getting closer and closer to some value like 4? And if they are, then we say that the limit is 4 for that function as x approaches a. Now, a will be given. A is usually, a lot of times it'll be given like x equals 2 or x equals 5. This is just a generic problem here. Next, let's look at the values in each of the f of x columns and determine whether the values seem to be approaching a single value. So we're talking about this column here and this column here. Do they seem to be approaching a single value as we move down each column? In our columns, we look at the sequence, of those numbers and so on, and the next set of numbers and so on. Although we have chosen the values to be a plus or minus 1/10, 100th, 1,000th, 1/10,000, and so forth, and these values will probably work nearly every time, on very rare occasions, we may need to modify our choices. And we'll see, I think we'll see an example of that coming up shortly. If both columns approach a common value, y value, L, we state that the limit as x approaches a of f of x is L. We can use the following strategy to confirm the result obtained from the table or as an alternative method for estimating a limit. Number 4, using a graphing calculator or computer software that allows us to graph functions. Desmos is a good graphing calculator. We can plot the function f of x, making sure the functional values of f of x for x values near a are in our window. We can use the trace feature to move along the graph of the function and watch the y value readout as the x values approach a. We might not be able to do that on, yeah, you might be able to do it on Desmos. Maybe we'll demonstrate that. If the y values approach L as our x values approach a from both directions, then the limit as x approaches a of f of x equals L. We may need to zoom in on our graph and repeat this process several times. Okay, so let's take a look at this function here. Now, this is supposed to be just reading of the textbook, but then I get kind of excited here and like to do more. So let's take a look here. X squared minus 4. And then what was it? X plus 2 on the bottom. X plus 2. And this is very basic anyways. So notice right here, this calculator, you can't see. Oh, and it was, let me just make sure. X minus 2 on the bottom. There we go. Notice you can't see the discontinuity at Oh, there it is. You can see it there. At 2, this function is undefined, right? But what we're saying there is as the x values, notice the x value here is 0.43 and 0.50 and so on. You can move this you can move this x value closer and closer to 2, and then what is happening to the y value? You see the y value getting closer, 3.96, 3.97. It's getting closer and closer to 4. And then from the left-hand side, values of, they also approach 4. All right, sorry about that. Somebody came into the office here. So we were looking at the limit as x approaches 2, and just kind of showing this graphically. If we take points on, values of x as we approach 2, we can see that the y values are approaching 4, right? And same thing from the left-hand side. As the x values get closer and closer to 2, the y values, they're above 4 in this case, but they're getting closer and closer to 4. But you see that the function is actually not defined to be 4 at x equals 2. But we still say that the limit exists here. All right, let's continue. Where were we? All right. So let's go ahead and take a look at the limit. And this is a special limit here. You might not know this function, but the limit as x approaches 0 of the sine of x over x. And well, let's take a look here because this is actually, this is actually kind of a cool function. The sine of x, so let's go to trig, sine of x over x. Well, yeah, we can tell by looking at the graph that as x approaches 0, the function values seem to be approaching 1, right? Even though this function is undefined when x is equal to 0, if you approach from the right-hand side, as x values approach 0, you can see the y value creeping up to the value of 1. And it looks like they actually hit it. It's probably approximately 1 here, not exactly 1, but it's close enough that it calls it 1. Now we can see this in just a table. If we choose the x values, here x is 0. So values that are approaching 0 are negative 0.1, negative 0.01, negative, keep going closer and closer to 0. And we see that these values are, let's see here, they look like they're getting closer and closer. Notice there's more 9s, right? We start with 0.99, 0.9999, and so on. And we get more, closer and closer to 0.999999999, which is, very close to 1. The same behavior happens on the right-hand side. As we have positive values that are getting smaller and smaller, the function values are getting closer and closer to 1. So the values in this table were obtained using a calculator and using all the places given in the calculator output. As we read down each column, we see that the values in each column appear to be approaching 1. Thus, it is fairly reasonable to conclude that the limit as x approaches 0 of sine of x over x equals 1. A calculator or computer-generated graph would be similar to that shown in figure 2.13, and it confirms our estimate. There it is. And actually, just keep this one in your head for a while. We'll come back to this one. We will show another way later in this class to find this limit and to show that it's, and we will show that it's equal to 1. Right, so, all right. Again, another function that we're finding the limit as x approaches 4 using a table of values. Okay, well, we're approaching 4, right? So we said we're going to take 4 and subtract 0.1, 4 minus 0.01, 4 minus, and so on. And these values will, if you do it in this pattern, these values will get closer and closer to 4. And so then you can look at the output values and see what those are doing. Okay, well, if we look at these, they're close to 0.25, 0.250, 0.2500, 3 zeros, 4 zeros. This looks like it's getting closer and closer to 0.25 or 1/4. Okay, remember that this function, at least this one here, this function is not defined at 4, because if you plug in 4 into the denominator, you get 0. Okay. On the right-hand side, from the right-hand side, for values larger than 4, but getting closer to 4. Okay, this is 4 plus a tenth, 4 plus 100, 4 plus 1,000. What is happening on this side? Well, these are 0.248, 0.249, 0.2499, 0.24999, and so on. It looks like we are approaching 0.25 as well, 1/4. So we would say that the limit as x approaches 4 of this function is 1/4. After inspecting this table, we can see the functional values less than 4 appear to be decreasing towards 0.25, whereas the functional values greater than 4 appear to be increasing towards 0.25. We conclude that the limit is 0.25, and we can look at the graph and make this estimate. Okay, of course, I personally like the graph, so we're in the graph, we are, moving in these directions, and the actual graph is doing this. Right? And so we are approaching this point, and we are interested in its y value. The function value there is 0.25. So you can try one on your own if you would like to do one of these problems. Might be a good exercise. At this point, we see from example 2.4 and 2.5 that it may be just as easy, if not easier, to estimate the limit of a function by inspecting the graph as it is to estimate the limit by using a table of function values. Yes, it's probably easier, I would think, to look at the graph. In example 2.6, we evaluate the limit exclusively by looking at the graph rather than by using the table of function values. So if you're not able to see it from the graph, that is a little bit of a problem, and you would want to, come to office hours and we can kind of try to discuss it some more. But here, we are evaluating the limit as x approaches -1 of this function g of x. We're not given a formula for g of x, so we can't even use a table of values here. What we want to do is let's look at the limit as we go from the left-hand side. What is this function approaching? It looks like it's approaching 3. Right? This is a y equals 3 here. What about from the other side? If we go approach -1 from the right side, what is this function doing? It looks like it's approaching a y value of 3. So we would say this is 3. Notice no table of values was needed. Despite the fact that g of -1 is equal to 4, notice that g is defined at -1, and it is defined to be 4, but the limit is 3. Okay, the limit and the actual function value don't necessarily need to be equal. Okay, we'll talk about this concept later in this class as well. But as far as we're concerned right now, they don't need to be equal. So as the x values approach -1 from either side, the g of x values approach 3. Therefore, the limit is 3. Now that we can determine this limit without even knowing the note that we can determine this limit without even knowing the algebraic expression of the function, right? We weren't explicitly given a formula for the function, but we can still find the limit by looking at the graph. Based on example 2.6, we make the following observation. It is possible for the limit of a function to exist at a point and for the function to be defined at this point, but the limit of the function and the value of the function at the point may be different, right? The limit was 3, the function value was 4. That's okay, I guess. We'll talk about something called continuity later in this class, and we will see that this function is clearly not continuous, but we'll define that later. Okay, you can do this problem here on your own. It's pretty simple just by looking at it. So next, continue in the reading here. Looking at a table of function values or looking at the graph of a function provides us with useful insight into the value of the limit of a function at a given point. However, these techniques rely too much on guesswork. We eventually need to develop alternative methods of evaluating limits. These new methods are more algebraic in nature, and we explore them in the next section. However, at this point, we introduce 2 special limits that are foundational to the techniques to come. Okay, so yes, we need something more algebraic in nature, right? just looking at a graph is not really the best thing, because what if I gave you the sine of 1 over x? Now what do you think the limit is? Right? You can zoom in if you want. You can try to zoom in, do your best here, and your computer will freeze, right? So, okay, so there's an argument for needing algebraic techniques, not just looking at pictures. But here are two very important limits. This is a theorem 2.1, so this is important. Let a be a real number and c be a constant. So the limit as x approaches a of the function x is a. Okay. Now this should be somewhat obvious. And let's go ahead and read the what it says there down there. We can make the following observations about these two limits. For the first limit, observe that as x approaches a, so if x is approaching a, notice the function here, f of x is equal to x. So if x approaches a, well, since x is f of x, then that means that f of x approaches a. And so the limit there must be a. Okay, so as x approaches a, so does f of x. Because f of x equals x, then this must be true. Okay, that's pretty nice. Next, number 2, the limit as x approaches a of the constant function c. I like to look at these as graphs. So, well, I could sketch it. I guess. Let's sketch a value c here, which could be like 2 or 1 or whatever. This is just a constant, it's just a constant horizontal line. So let's let a be equal to, just whatever value. What if we approach a from the left-hand side? Notice this function is constantly has the value c. If we approach from the right-hand side, well, this function is always, constant. It has a value of c. So what is going to be this limit? It's going to be c. So that's what it is. And you can take a look at a table of values. This function is always c. So, for values less than a or greater than a, does anybody see a pattern in these output values? Yeah, they're all approaching c. You could say they're all actually equal to c. All right. So very nice. Observe that for all values of x, regardless of whether they are approaching a or not, the values f of x remain constant at c. We have no choice but to conclude that the limit as x approaches a of c equals c. The existence of a limit, and this is what we were talking about a moment ago. As we consider the limit in the next example, keep in mind that for the limit of a function to exist at a point, the functional values must approach a single real number value at that point, right? So if the functional values do not approach a single value, then the limit does not exist. Okay, so basically what we're saying here is a limit might not exist. And what's one way that the limit could not exist? If the functional values do not approach a single value, right? In our first example, the function values were approaching 4, both on the left and the right, but maybe they won't. So let's take a look at the limit as x approaches 0 of the sine of 1 over x using a table of values. And so we're approaching 0 here. So we're going to take numbers that are smaller than 0 and getting closer and closer to 0. Okay. Well, let's take a look at the trends here. We have 0.54, then 0.50, then a negative 0.82, then a positive, then a negative, and then a positive number. So this thing kind of seems to be bouncing all over the place. If we take a look at the other side, these are values that are all greater than 0 and approaching 0. So what are the outputs? Negative 0.54, negative 0.50, and then a positive number, and then back to negatives, and then back to positives, back to negatives. So we have some oscillation going on here. This is the graph that I showed earlier, actually. And we see that, yeah, this thing is definitely oscillating. So does this have a limit? Well, it's not clear if there is a limit or if it doesn't seem like there's a limit. Now, after examining the table of function values, we can see that the y values do not seem to approach any one single value. It appears the limit does not exist. Before drawing this conclusion, though, let's take a more systematic approach. Take the following sequence of x values approaching 0. So here, you don't have to know exactly where they got them from. You can come to office hours if you want more information on this. But these values here are all positive, and if you look at them, they're denominators. The denominators are increasing, which means the fractions are decreasing. So these are decreasing and approaching 0. And then if you take a look at the corresponding outputs, you see that they are +1, -1, +1, -1. So this function is oscillating back and forth, and therefore it is not approaching a single value. And that was the condition that we highlighted up above. If the functional values do not approach a single value, then the limit does not exist. At this point, we can indeed conclude that the limit as x approaches 0 of sine of 1 over x does not exist. Mathematicians frequently abbreviate this DNE, which we'll use that in our class a lot. DNE for does not exist. Thus, we would write the limit as x approaches 0 of the sine of 1 over x, DNE. The graph of f of x equals sine of 1 over x is shown in figure 2.17, and it gives a clear picture of the behavior of sine of 1 over x as x approaches 0. You can see that sine of 1 over x oscillates ever more wildly between -1 and 1 as x approaches 0. Okay. 2.6 would be a very good exercise to take a look at if you feel like doing that. All right. One-sided limits. Sometimes indicating that the limit of a function fails to exist at a point does not provide us with enough information about the behavior of the function at that particular point. To see this, we now revisit the function g of x equals the absolute value of x minus 2 over x minus 2, introduced at the beginning of this section. As we pick values of x close to 2, so values of x close to 2, g of x does not approach a single value. So the limit as x approaches 2 does not exist. Right, so we would say DNE for this limit as well. However, this statement alone does not give us a complete picture of the behavior of the function around the x value 2. To provide a more accurate description, we introduce the idea of a one-sided limit. For all values to the left of 2, or the negative side of 2, g of x is equal to -1. Thus, as x approaches 2 from the left, g of x approaches -1. Mathematically, we say that the limit as x approaches 2 from the left side is -1. And we're going to express this symbolically as the limit as x approaches 2 with a little negative sign above as a superscript on that 2. This is the limit as x approaches 2 from the left side of the function g of x, and this is equal to -1. What about the right-hand side? Let's go ahead and click and go to the link. Do they show the graph? No, they don't. Okay, so let's go back and take a look at this. What page are we on? 152. So we'll be back. But this is what they're talking about here. As the x values approach 2 from the left-hand side, okay, well, this function is constantly -1. We approach a y value of -1 from the left-hand side. Now, from the right-hand side, we don't approach the same y value. We actually approach the number +1 from the right-hand side. So we're defining the limit of this function from the left-hand side to be -1, and we're similarly going to define the limit as x approaches 2. From the right-hand side, we use a little plus sign of this function g of x. This is going to be equal to +1. And that's what's given in the next statement. Similarly, as x approaches 2 from the right, or from the positive side, g of x approaches 1. Symbolically, we express this idea as the limit as x approaches 2 from the positive side of g of x equals 1. We can now present an informal definition of one-sided limits. We define two types of one-sided limits. From the, there's going to be one from the left and one from the right. Excuse me. Limit from the left. Let f of x be a function defined at all values in an open interval of the form CA. So here what we're doing is we're just saying, okay, well, if this is A, then we're going to define some value C here. And maybe I'll draw a similar picture to the one that was drawn earlier. Something like this. So, okay, we're defining this function f of x, and we're saying that it's defined on an open interval of the form CA. So it's defined starting at some value C all the way up to some value A, not necessarily including A. Let L be the real number. Let L be a real number if the function f of x has values that approach the real number L as the values of x, where x is less than A, approach the number A, then we say that the limit L is the limit L, that is the limit of f of x as x approaches from the left. Symbolically, we express this idea as the limit as x approaches A from the left of f of x equal to L. Apologies again, my computer is running out of battery. So so let's take a look at this general picture here. Basically, what we're saying is, as these x values, these are all x values less than A if we're approaching from the left-hand side. And so we approach from the left-hand side, and we're saying that if these function values, these are all the function values here, and it looks like they are approaching some number L. In this case, this L is going to be some positive number, whatever that positive number is here. But if we approach that value on the left-hand side, then we will say that the limit of this function as x approaches A from the left-hand side is L. And let me then do another one. I'm going to call this one M here up above. And the second portion of this function is a little bit higher. So let's look at the limit from the right. And let's do it in purple, actually. From the right, let f of x be a function defined at all values in an open interval of the form AC. And C can be, I'm just going to make another C, I'll call it C1 here. And so, it needs to be defined on some interval to the right of A. So, okay. And let L be a real number. In this case, I'm calling it M. If the values of the function f of x approach the real number M as the values of x, where of course x needs to be greater than A, approach the number A. So if we take values of x and we start plugging in closer and closer to A, then if the function values are approaching a value, let's call it M, then we say that the limit as x approaches A from the right of this function f of x is M. Okay. All right. Evaluating one-sided limits. So one place where this could come up a lot is, piecewise functions. So for the function f of x equals x plus 1, if x is less than 2, and they really like, so I like using graphs here. They use tables, which are fine too. I mean, they're a good tool, but the second rule is x squared minus 4 if x is larger than or equal to 2. Evaluate each of these limits. And of course, we want to look at the limit as x approaches 2 from the left and from the right. So from the left, let's start with this table. Why not? Let's do it. Let's use this table. So 2 from the left. So we got values that are less than 2, but these are getting closer and closer to 2, right? So we plug these in using a calculator into the function for this first rule here, because these are all less than 2. Then notice we got 2.9, 2.99. We see that we're approaching 3, it looks like. So pretty confidently here, we can say that the limit as x approaches 2 from the left of this function f of x is equal to 3. Now the right-hand side are values that are close to 2. They're getting closer and closer to 2 actually, but they're all above 2. And so for the numbers above 2, getting closer and closer to 2, we have 0.41, 0.0401, 0.004, 0004. We're getting close to 0 here, it looks like. And so that's what we see from the table as we approach from the right-hand side, this function. As we approach 2 from the right-hand side, this function looks like it's getting closer and closer to 0. Let's verify using the graph. Based on this table, we can conclude the limit from the left-hand side is 3. The limit from the right-hand side is 0. Therefore, the two-sided limit of f of x does not exist at x equals 2. Remember that in order for the limit as x approaches 2 of this function, notice I did not put a plus sign or a negative sign up here. We're not talking about a one-sided limit, but the limit, the original limit. This does not exist because we said that in order for this general limit here to exist, our function needs to approach the same value L from both the left and the right. And since these values 3 and 0 are different, then the limit does not exist. And when I say the limit does not exist, we're talking about the limit that where it's not the two-sided limit does not exist. Okay, figure 2.18 shows a graph of f of x and reinforces our conclusion about these limits. Right, okay, very good. Very nice, very nice. Okay, how many more pages do we have? Oh, these videos turn out to be pretty long. Oh my gosh, all right. All right, we're almost done. All right. Let us now consider the relationship between the limit of a function at a point and the limits from the right and left at that point. It seems clear that if the limit from the right and the limit from the left have a common value, then that common value is the limit of the function at the point. This is a very important idea here. It seems clear that if the limit from the right and the limit from the left have a common value, then that common value is the limit of the function at that point. Similarly, if the limit from the left and the limit from the right take on different values, then the limit of the function does not exist. These conclusions are summarized in relating one-sided and two-sided limits. And this was one of the learning objectives at the beginning of the section. So the limit as x approaches a of f of x is equal to L if and only if the limit as x approaches a from the left of f of x equals L, and the limit as x approaches a from the right of f of x is also L. So both of these limits need to be equal to the same number, and only in that case where both of these are equal to the same number does the two-sided limit exist and is equal to the same number. So theorem 2.2, let f of x equal, or let f of x be a function defined at all values in an open interval containing a, with the possible exception of a itself, and let L be a real number. Then the two-sided limit exists and is equal to L if and only if the left-hand limit is equal to L and the right-hand limit is equal to L. All right, very important. Infinite limits. Evaluating the limit of a function at a point or evaluating the limit of a function from the right and left at a point helps us to characterize the behavior of a function around a given value. As we shall see, we can also describe the behavior of functions that do not have finite limits. We now turn our attention to h of x equal to 1 over x minus 2 squared, the third and final function introduced at the beginning of this section, see figure 2.12c. Okay, so let's go ahead and take a look at it really quick. Here, we'll go back. This is the first page here. Notice that here, the function right, this side here, the function does not seem to be approaching a single finite value L. It looks like as we approach 2, this function actually goes off to infinity. So if it goes off to infinity, what can we define the limit of the function to be? Let's go ahead and head back there. From its graph, we see that the values of x, as the values of x approach 2, the values of h of x become larger and larger, and in fact become infinite. Mathematically, we say that the limit of h of x as x approaches 2 is positive infinity. So symbolically, yeah, this is kind of probably what you expected. As x approaches 2 of this function equals positive infinity. More generally, we define infinite limits as follows. And so here are the very formal definitions. Let's go ahead and maybe we'll go through them. We define 3 types of infinite limits. Infinite limits from the left. There are infinite limits from the right, and the 2-sided infinite limit. So these are all very similar, but because they're slightly different, they feel the need to define each one of them separately. So we'll go over maybe one of them and let's see if we can give an example. Let f of x be a function defined at all values in an open interval of the form BA. So let's go ahead and define BA. If the values of f of x increase without bound as the values of x, where x is less than a, approach the number a, then we say that the limit as x approaches a from the left is positive infinity. So if we have a function something like this, it looks like the limit as x approaches a from the left of this function is positive infinity. Okay. If the, let's use a different color for number 2. If the values of f of x decrease without bound as the values of x, where all of these values are less than a, approach the number a, then we say that the limit as x approaches a from the left is negative infinity, right? So what if we have a function that does this? Now it's a very similar limit, but they define them separately there. Okay, and then this would be our notation here. Okay, what about from the right? Well, we can we're not going to read them all. If if there's a function that does this, I'll delete the other side here. From the right, for that function in black, we would say the limit as x approaches a from the right of this function is positive infinity. For the one in red, of course, as we approach from the right, the value of a, the function values f of x approach negative infinity. Same stuff. Now the 2-sided infinite limit, that's basically if the function, let's say there is a function like the one in black here, and if that function approaches positive infinity from both sides, from both the left and the right, then we say that the limit as x approaches a is positive infinity. So let's read it here. Let f of x be defined for all x not necessarily equal to a, but in an open interval containing a. So let's suppose that, let's put a C here. There's a function defined on an open interval around a. If the values of f of x increase without bound as the values of x approach the number a, then we say that the limit as x approaches a is positive infinity, and this is what we write. Okay, so this is just, now it's happening from both sides. If the values decrease without bound, then we would say in part 2, the limit is negative infinity. All right, it is important to understand that when we write statements such as the limit as x approaches a of f of x equals positive infinity, or the limit as x approaches a of f of x is negative infinity, we are describing the behavior of the function as we have just defined it. We are not asserting that a limit exists for the limit of a function to exist. So this is a kind of a nuanced thing here. But in both of these cases that are given, we are asserting that we are not asserting that a limit exists, because for the limit of a function f of x to exist at a, it must approach a real number L as x approaches a. Okay, so infinity is not a real number, right? It's not a number, it's, the increasing without bound of numbers. So that said, if, for example, the limit as x approaches a of f of x equals positive infinity, then we will always write that the limit as x approaches a of f of x is equal to positive infinity, but we won't write that it does not exist, right? It's still preferable to describe the behavior of the function near x equals a, but we are not saying that a limit exists. This is notation to say that the limit goes to infinity, and it is not a finite real number L. Okay. All right. Very nice. Now this happens a lot, of course, with rational functions. Evaluate each of the following limits if possible. Use a table of function values and graph f of x equals 1 over x to confirm your conclusion. Right. So I love using the graph. The graph of the function f of x equals 1 over x looks like this. This is the x-axis and the y-axis. And so the limit, let's look at the left, or the first part here. The limit as x approaches 0. So as we approach 0 from the left, what is the function doing? It looks like it's going down to negative infinity. So this would be negative infinity. And you can see from the function values here, okay, we're getting closer and closer to 0 from the left-hand side. If you look at these values, they're negative 10, negative 100, negative, and these are increasing negatively without bound. So we would say negative infinity. What about from the right-hand side? Well, from the right-hand side, if we go, look at x values approaching 0 from the right-hand side, what is the function doing? The function is going to, it looks like positive infinity. This is going to be positive infinity. All right, and then we can see that in the table of values or in the graph of the function. And so what does that say about the limit here in part C? The limit, the two-sided limit as x approaches 0, these are not approaching the same value or the same, infinity. So we would say this does not exist. Okay? Because one is going down, the other is going up. Since they're not the same, we say the limit does not exist. Okay, so part A, the values of 1 over x decrease without bound as x approaches 0 from the left. So we conclude that the limit is negative infinity. The values of 1 over x increase without bound as x approaches 0 from the right. We conclude that the limit is positive infinity. And then since those two limits, this one and that one, have different values, we conclude that the limit does not exist. The two-sided limit as x approaches 0 of 1 over x does not exist. The graph confirms this. Try 2.8 on your own. That would be pretty nice. It's a little bit different, but it's similar. It is useful to point out that functions of the form, so of the form f of x equals 1 over x minus a to the n, where n is a positive integer, have infinite limits as x approaches from either the left or the right-hand side. You may have seen functions like this in the past. And there are actually two cases. If n is an odd integer, then you have this behavior where one side goes down to negative infinity, the other side goes up to positive infinity. If n is an even integer, then both sides go up to positive infinity. Okay, so then we have these limits. You can tell by looking. I'm going to go to theorem 2.3 in the box. If n is a positive even integer, then the limit, and notice that this is a two-sided limit, the limit as x approaches a of this function is positive infinity. You can see both sides here go to positive infinity. So, of course, the left-handed limit and the right-handed limit, each independently, are also positive infinity. Now, if n is a positive odd integer, then the behavior from the right-hand side is positive infinity, that the function goes to positive infinity, and we can see that right there. And then the limit as x approaches a from the left-hand side is negative infinity, and we can see that here. Okay. So then the two-sided limit, of course, does not exist. We should also point out that in the graphs of f of x equals 1 over x minus a to the n, points on the graph having x coordinates very near to a are very close to the vertical line x equals a. Okay, one more time. We should also point out that in the graphs of f of x equals 1 over x minus a to the n, points on the graph having x coordinates very near to a are very close to the vertical line x equals a. Yeah, so you can see the vertical line is the red dashed line that they put in each of those. So if you were to get a point, I'm not sure how well this will show up, but I'll use a purple dot here on the graph. If you were to plug in some x value near a, well, the y value, I'm gonna map it here. The y value is going to be, a fairly large value. And as you get closer and closer to a, let's choose another value, say right here for a. Well, then the y value is going to be really large, right? Somewhere way up there. So as you get closer and closer to a, the function values, those points get closer and closer to the vertical line at x equals a. That is, as x approaches a, the points on the graph of f of x are closer to the line x equals a. The line x equals a is called a vertical asymptote of the graph. You've probably heard of this before. And so now we can formally define vertical asymptotes in terms of limits, right? So this is probably something that you may not have defined in your pre-calculus class. So definition, let f of x be a function. If any of the following conditions hold, then the line x equals a is a vertical asymptote of f of x. So if, let's start with the first one, the limit as x approaches a, so let's choose a to be this one here, and we'll choose x equal a to be there. If the limit as x approaches a from the left of f of x is equal to positive infinity or negative infinity, I'm just going to use positive for the example here. If the limit of this function f of x as x approaches a is positive infinity, then we say x equals a is a vertical asymptote. What about from the right-hand side? Yeah, if from the right-hand side, my function f of x approaches either positive or negative infinity, then we say that the line x equals a is a vertical asymptote. And of course, if the two-sided limit exists as well, then we say that x equals a is a vertical asymptote. That's kind of nice. Something that you've known about before, vertical asymptotes are now defined in terms of limits. So example 2.10, find a vertical asymptote. Evaluate each of the following limits using infinite limits from positive integers. Identify any vertical asymptotes of the function 1 over x plus 3 raised to the 4th. And so do they give us the graph? No, they don't. But we can graph this. 1 over x plus 3, that means that at negative 3, something funny is going to happen. This is a even positive exponent. So this function is going to look something like this. Okay. And so that means that there's going to be a vertical asymptote here. Okay. And we can verify this. While the limit as x approaches negative 3 from the left looks to be positive infinity, the limit from the right looks to be positive infinity, and the limit, the two-sided limit, exists this time and is positive infinity. Oh, they're written right here. So the function f of x has a vertical asymptote just by the first one of these statements being the way it is, the fact that the limit is positive infinity. That means automatically that there is a vertical asymptote at x equals negative 3. All right. In the next example, we put our knowledge of various types of limits to use to analyze the behavior of a function at several different points. And so this is a very good example here. And this is one that maybe I think we might do in our lecture slides, but you should definitely try to do yourself. Pause the video, write all of these down. There's, quite a few, maybe like 12 questions here, but they're simple. The answer is, just a single number or DNE. So let's go ahead and take a look at it. The limit as x approaches -4 from the left. So from the left, if we approach -4, it looks like our limit there, the function is approaching 0. So we'll put a 0 under it. What about the right-hand side? The right-hand side, as we approach -4 from the right, this function is approaching 0 as well. So then the double-sided limit is going to be 0 because they're both existing and equal. And then f of -4, it looks like the function is actually defined at -4, and it's defined to be 0. Okay, very nice. Behaved well there. We would say that the function is actually continuous there. We'll talk about that later. What about at -2? As x gets closer and closer to -2, the function looks like it's approaching the value of 3. What about from the other side? As we approach -2 from the right-hand side, oh, it looks like the function is approaching 3 as well. So the double-sided limit is going to be 3. Since these two are equal to each other, the double-sided limit is going to be the same value, 3. And then now this is what about the function value, f of -2? F of -2 here looks like it is undefined at that point. All right. What about at not 1, at 1? As we approach 1 from the left-hand side, it looks like we're approaching the value of 6. Then as we approach from the right-hand side, the function is defined down here. It's a piecewise function, so it looks like we're approaching 3 from the right-hand side. So what is the double-sided limit? The double-sided limit does not exist because the single-sided limits are not equal to each other. And then finally, what is the function value? F of 1. F of 1, you can see there's a closed circle up there at 6. So f of 1 is 6. Okay, and then the last one, part D. The limit as x approaches 3 from the left. As we approach 3 from the left, it looks like this thing is shooting off to -infinity. So this would be -infinity. Then, what about as we approach 3 from the right? Well, this thing is shooting off again to -infinity from the right side. This is -infinity, the double-sided limit then, therefore it must be -infinity. It's just the same as these two if they are equal. And then f of 3, what is f of 3? It is undefined. The function is not defined at 3. Okay, and then we can verify that all of those values are correct just by looking at the graph. All right. And then there's 2 problems here. Oh, no, this is a sample problem here. Try this one on your own, see if you can figure that one out. All right, and we are not going to go over Einstein's equation. This is the chapter opener. You can take a look at it, read it yourself if you like. We are done. That was a long video. And if you're still here, make sure to, like the video. So I know somebody's watching. All right. Well, hopefully that helps. This is a really nice example here at the end. So if you stuck around, you got a little bonus. All right. Bye for now.